Welcome everyone to our lecture on force convection heat transfer, an important process in thermal engineering. Force convection occurs when a fluid is driven over a surface by external devices like fans or pumps, enhancing the heat transfer between the fluid and the surface. This mechanism is crucial in applications such as automotive cooling, air conditioning, and industrial heat exchangers. Unlike natural convection, which relies on density differences, forced convection uses controlled fluid motion to achieve higher heat transfer rates. Today, we will explore Newton's law of cooling, the governing equation, the dimensionless numbers, and how forced convection applies to the flat plates and pipes. We will also discuss its practical applications in everyday's and industrial systems. By the end, you will understand how fluid velocity and properties influence heat transfer and how engineers leverage forced convection for efficient thermal management. So let's explore into the fundamentals and see how external fluid motion shape the heat transfer in the world around us. Let's begin the basics of forced convection. The forced convection occurs when the fluid, such as air or water, is moved over a solid surface by an external device, like a fan, pump, or compressor. This motion enhances the heat transfer by carrying away the heat from or to the surface more effectively than natural convections. It's widely used in industrial applications, including the heat transfer in power plants, cooling systems in the cars, and HVAC systems in buildings. The heat transfer rate in forced convection depends on the factors such as fluid velocity, fluid properties such as viscosity and thermal conductivity, and the surface geometry. For example, faster airflow over a surface increases the heat removal as seen in the computer's cooling fan. Forced convection is essential for the systems requiring rapid and uncontrolled heat transfer, making it important in thermal engineering. Understanding how to manipulate the fluid flow allows engineers to optimize energy efficiency and the system performance. So let's move to the Newton's law of cooling to quantify this process. The Newton law of cooling is the foundation for analyzing this forced convection heat transfer. It states that the heat transfer rate Q is given by Q is equal to H into A into Ts minus T infinity, where H stands for convective heat transfer coefficient in watts per meter square Kelvin. A is the surface area in meter square, and Ts is the surface temperature, and T infinity is the fluid temperatures. The convective heat transfer here, H, is very much crucial as it reflects the efficiency of heat transfer and varies with the fluid type and flow conditions. Typically, H values for the forced convection ranges from 25 to 300 watts per meter square Kelvin, which are for the gases, and 100 to 40,000 watts per meter cube for liquids. Significantly higher the free convection or these values are higher as compared to natural convections due to the enhanced fluid motion. For example, in a car radiator, the forced airflow increases the heat transfer coefficient H, and which improves the cooling performance. This law allows the engineers to calculate heat transfer in systems like heat sinks or air conditioners. By understanding the heat transfer coefficient H and its dependence on the flow, we can design systems that maximize the heat transfer while minimizing the energy usage. Next, we will explore the types of the force convections. Force convection can be categorized into two main types. One is the external and other is the internal. External force convection occurs when a fluid moves over a solid surface, such as a wind blowing over a car's hood or the air force over the heat sink by a fan. This type is common in cooling applications where the fluid is in open contact with the surface. Internal force convection, on the other hand, involves the fluid flowing inside a confined space, like coolant moving through radiator tubes or the tubes in the pipes heat exchangers. This type is critical in systems requiring efficient heat transfer within ducts or pipes. Both types rely on the external devices to drive the fluid motion, enhancing the heat transfer compared to natural convection. For example, in a car's cooling systems, the internal convection in the radiator tubes and the external convection over the radiator fins works together. Understanding this distinction helps the engineer to design systems tailored to specific needs, whether the cooling of the electronics or the heating of the buildings. So let's look at the governing equations that describes the force convections in the next slide. The dimensionless numbers, which are very crucial in analyzing the force convections. As in the previous lecture, we have seen the Nusselt number, which represents the ratio of convective heat transfer to the conductive heat transfer, in which H is the convective heat transfer coefficient, and L is the characteristics length, and Kf is the fluid's thermal conductivity. A higher Nusselt number indicates a stronger convection. The Reynolds number, as we know, determines the flow type, whether it is a laminar or the turbulent, which is based on the fluid's velocity, density, and viscosity, and the length scale. When there is a turbulent flow, it is going to enhance the heat transfers due to the increased rate of mixing. The Prandtl number, as we all know, it is a ratio of momentum diffusivity to the thermal diffusivity, which also reflects how momentum and heat is spread in the fluid. As we all know, the Nusselt number is a function of the Reynolds number and the Prandtl's number, so it allows us to correlate the flow conditions with the heat transfer. For example, in a heat exchanger, a high Reynolds number indicates a turbulent flow, which increases the value of Nusselt number and the heat transfer coefficient H. These numbers simplify the complex convection problems, guiding the design of efficient systems like the radiator or the cooling fans. So let's apply this to the heat transfer over a flat plate in the next slide. Force convection is governed by several fundamental equations. The first is the continuity equations, which is given by d rho by dt plus del dot rho multiplied by v is equal to 0, which is a mass conservation, which states that the fluid's density and velocity balances in the flow field. For steady flow in the pipes, it simplifies to A1 V1 is equal to A2 V2, where A is the cross-sectional area and V is the velocity. The energy balance equation Q is equal to m dot Cp multiplied by delta T relates the heat transfer to the total mass flow rate m dot and specific heat capacity Cp and temperature change delta T. The momentum equation or the Navier-Stokes equations also describe the fluid motion under the pressures, viscosity, and external forces. These equations capture the interplay of the fluid dynamics and the heat transfer in a forced convection. For example, in a pipe, the continuity equation ensures the consistent flow while the energy balance calculates the heat absorbed by the coolant. Solving this equation often numerically allows engineers to predict flow and heat transfer behavior in systems like the heat exchanger or cooling duct. Next, we will explore the dimensionless numbers that simplifies this analysis. Heat transfer over a flat plate is a classic case of external force convection. The Nusselt number correlates the heat transfer coefficient H to the flow conditions. For laminar flow, when Reynolds number is less than 5 into 10 raised to 5, Nusselt number is given by 0.332 multiplied by Re raised to 1 by 2 into Pr raised to 1 by 3, where Reynolds Re is the Reynolds number and Pr is the Prandtl number. For turbulent flow, Re, which is greater than 5 into 10 raised to 5, the Nusselt number is given by 0.0296 multiplied by Re raised to 4.5 or 4 by 5 multiplied by Pr raised to 1 by 3. These correlation allow us to calculate H, which determines the heat transfer rate via Newton's law of cooling. Laminar flow has a smoother, less efficient heat transfer, while the turbulent flow enhances the mixing, which causes the increase in the value of heat transfer coefficient H. For example, the air forced over a flat electronic board follows this correlation, guiding the cooling system design. These formulas are used in the applications like heat sinks, solar panels, or industrial drying process. By understanding how Nusselt number depends on Reynolds number and Prandtl number, engineers can optimize the heat transfer for specific flow condition, ensuring efficient cooling or heating. Next, we will explore the forced convection inside the pipes, which is the another key application. The forced convection inside a circular pipe is critical for systems like heat exchangers and radiators. The heat transfer coefficient H depends on the flow conditions. For laminar flow with constant wall temperature, the Nusselt number is a constant at Nu is equal to 4.36, indicating a fully developed thermal profile. For the turbulent flow, when the Reynolds number is greater than 2300, the Nusselt number is given 0.023 Re raised to 0.8 multiplied by Pr raised to 0.4, reflecting the enhanced heat transfer due to mixing. These correlations allow the engineers to calculate the heat transfer coefficient H and predict the heat transfer rate inside the pipes. For example, in a car radiator, the turbulent flow of the coolant through the tube increases the Nusselt number, improving the heat removal from the engine. The choice of laminar or a turbulent flow depends upon the pipe diameter, fluid velocity, and the desired heat transfer rate. These formulas are used in designing HVAC ducts, oil pipelines, and industrial cooling systems. By analyzing the flow regimes and applying these correlations, engineers can optimize the pipe designs for the efficient thermal performance. Next, we will look at the practical applications of forced convections in the engineering systems. To summarize, the forced convective heat transfer enhances the heat exchange by using the external forces to drive fluid motion over the surfaces or through pipes. Governed by Newton's law of cooling, it depends on the fluid properties, velocity, and geometry. Dimensionless number like Nusselt number, Reynolds number, and the Prandtl number simplify this analysis, correlating the flow condition with the heat transfer efficiently. We have explored the external convection over a flat plate and internal convection in the pipe using the correlations given by Nusselt number, Reynolds number, and Prandtl number for a turbulent pipe flow. Applications include automotive cooling, air conditioning, heat exchangers, and electronic cooling, where forced convections ensure efficient thermal management. This process is vital for improving the energy efficiency, safety, and performance in the industrial and everyday systems. I hope these lectures have deepened your understanding of forced convections and its impact. For the next time, consider how forced convection applies to a system you encounter like a car radiator or a laptop fan. Thank you, and let's continue exploring the science of heat transfer. Forced convection is integral to many engineering applications. In automotive cooling systems, radiators use forced convection to dissipate engine heat, with the fan driving over fins and the coolant flowing through the tubes. The air conditioning and refrigeration systems rely on forced convection to transfer heat via evaporators and condensers, ensuring efficient cooling. Heat exchangers in industries such as power plants or chemical processing use forced convection to transfer heat between the fluids, often through tube bundles or the plate systems. Cooling of electronic components like the computer chips or the LEDs depends on the forced convection through heat sinks and fans to prevent overheating. These applications highlight the versatility of forced convection in managing the thermal energy. By leveraging fluid motion, engineers achieve high heat transfer rates, improve system performance, and energy efficiency. Whether it's keeping engine cool or maintaining comfortable indoor climates, forced convection is a very critical for that. So let's conclude with the summary of forced convective heat transfers and its significance.